Okay, we started recording. So it's n times 1, 1 f. Okay. So is this okay? I'm just defining, given a phi, which is a positive extended real valued measurable function. I define, you can take either of these two definitions. The first one I have defined it explicitly, that when the hello, say it again. Okay, someone said something, I didn't hear. Anyway, when the range phi x is between this I minus 1 by 2 power n to I by 2 power n, then we define it to, we take it to be the I minus 1 by 2 power n. Or you can take the inverse image of this interval through phi and then call that as ENI. And in that set, on that set, you define it to be I minus 1 by 2 power n. And on the other set where when phi of x is greater than n, in that set you define it to be n. Okay.
So this set Fni is essentially dependent on n, right?
Yeah,
the set Fni.
Exactly. It essentially, yes, that doesn't depend on I. Correct. Sorry, there is no. Yeah, that just depend on Fn. Right. There is no I. So I is for the other things. Right. Okay. So this is well defined. Now we want to say that this is our required phi n. Okay. First we want to verify. So first claim 1. Phi n are increasing. Okay. So how do you verify phi n is increasing? We just have to verify phi n x is smaller than phi n plus 1x for all x. So suppose we take a x in x, and suppose x is in this interval, I minus 1 by 2 power n and I by 2 power n. Okay. Suppose it is in this interval. Okay. For I is between n to power n greater than equal to 1. Okay. So then phi nx equal to, what is phi nx? Which is just we have defined it to be this. Okay, now we verify what is phi n plus 1 by x. What is phi n plus 1x? So x is here. So x is in this interval. You can write the same thing as 2i minus 2 by 2 power n to 2ai by 2 power n. Right? 2i. This is not 2 power I, 2i. I'm just multiplying by, 2 power n plus 1. Here in the bottom, 2 power n plus 1. Right? I just maybe I'll write it again. X is in this interval. 2i minus 1 by 2 power n plus 1. 2i by 2 power n plus 1. Okay? If x is in that interval, it's same as this interval. But this interval, it is joint union of these two things. 2i minus 2 power n plus 1. 2i minus 1 2n plus 1. Okay? Union 2i minus 1 power n plus 1. 2i by 2 power n plus 1. Okay? Now if x is here, then phi n plus 1x equal to same as, which is same as I minus 1 by 2 power n. Okay, I don't want to write it like that, which is equal to phi nx. Okay. If x is here, okay, then phi n plus 1x equal to 2i minus 1 by 2 power n plus 1, which is of course greater than I minus 1 by 2 power n. Okay. So we have verified that phi n plus 1 x is greater than or equal to phi n x. Okay. I have just verified that phi n Pn is increasing when x is in this interval. So if x is greater than n, greater than or equal to n, for that also I have to verify. So if further x is greater than or equal to n plus 1, then of course phi n plus 1x equal to n plus 1. That's how we have defined it, okay, which is greater than n, which is equal to phi nx. Of course, x is greater than n plus 1 means x is greater than n, so which is equal to phi nx. So we have verified that phi n is increasing when x is greater than n plus 1. So if x is between x is less than n plus 1 and greater than or equal to n. Okay, here we have to verify that it is increasing. So now this, suppose, I mean, what does it mean? Now suppose x is in some I minus 1 by 2 power n plus 1 into I by 2 power n plus 1. Then this I by 2 power n plus 1 has to be less than or equal to n plus 1. So I by 2 power n plus 1 has to be, there is only one choice, right? I has to be greater, sorry, it should be greater than n. Why is it happening? It should be greater than n. So I, this is 2 n plus 1. I mean, we have assumed that it is greater than or equal to n. So this implies I by I is greater than n to power n plus 1. So no, sorry, that should be strictly greater than that. So this implies there is only one choice. I is equal to n plus 1 to power n plus 1. Right? That's the only choice. So if we have x is between them, then x is in this interval, which is that. Okay, let's just write it. I minus 1 by 2 power n plus 1, I by 2 power n plus 1 with I equal to n plus 1 2 power n plus 1. So then we know that what is phi n plus 1x, which is just this value. Which is n plus 1 2 power n plus 1 minus 1 divided by 2 power n plus 1, which is equal to n plus 1 minus 1 by 2 power n plus 1, which is greater than, this is some positive number, which is greater than n, which is equal to phi n. Okay, so we have verified that phi n is increasing. Is this clear? Did I go fast? I have just verified using the whatever we have defined using the definition. I have verified that it's increasing. Okay, is okay?
Okay, sir.
Okay. So I have
Yes,
just
fine.
directly verified that it is increasing. Okay, I have written all the details. You can pause the video and look at it if I don't send the file. If I send the file, then you can directly do that. Okay, now phi n is increasing. Now we want to show that it converges. Okay, now phi minus, let us say phi n is increasing. Phi n is phi minus phi n. So is less than or equal to, I mean, phi of x minus phi n x is less than or equal to 1 by 2 power n if x is in one of these intervals, I minus 1 by 2 power n, I by 2 power n. Okay. So, I mean, I can just remove it. I can just say that if x is less than n, so not x is less than n, sorry. If phi n x is less than n, okay, not phi n x, phi is less than n, right? Okay. So Do I need? Can it be extended real value? That may be a problem. No? I have to say that how can it be extended real value function? If phi of x is infinity, then we may have to.
So if phi of x is infinity,
Hmm.
then
Then phi and x will increase to infinity, no?
exactly, yeah.
Right. So that's not a problem. So yeah. So let's assume that that's right. If phi of x is infinity, so that's something. So first thing is if phi of x equal to infinity, then we know that phi and x will be always phi and x equal to n, right? Which will increase to infinity. That's no problem. Okay. So if phi and so otherwise, if phi of x is less than n, so then phi of x used to be less than n for some n at some point. Okay. So then after that n, phi of x minus phi n x is less than 1 by n. So this implies phi n x increases to phi of x. Okay. For all x. That's right, no?
Yeah, this is fine. Yeah.
This is fine. So I mean, if x is phi of x is not equal to infinity, then phi of x has to be less than n for some n. After that n, phi of x minus phi n x is less than 1 by n. So it will converge. Okay. So we have proved that. So this we have proved that phi n x increases to phi of x for all x. Okay. Now we have to verify that it converges uniformly. The statement of the theorem is it converges uniformly when it is bounded. So that is also clear. If phi of x is less than n, then there exists a n, and I mean there exists n such that maybe called n naught, okay, less than n naught. Then phi of then maybe we are going then for all n greater than or equal to n naught, phi n x, phi of x minus phi n x is less than 1 by 2 power n for all x. Okay. So after some time, this holds for all x. Okay. So this implies phi n x increases to phi of x. Or convergent, whatever you want to say. Converges to phi of x uniform. Okay. So we have proved the proposition, right? Is okay?
Yes, sir.
Okay. So we have proved the proposition. That's fine. So let us go ahead and define the let us define the integral. So right. Okay. So how do we define the integral? First, we want to define it for a simple function. So after defining for a simple function, we want to define it for any measurable, positive measurable function. So let phi is a simple function, okay, s of x. That is phi from x to 0 infinity. We take extended real value function. So it may take the value infinity, but that will be on a measurable set. It's only positive infinity. So there is no problem of adding infinity and subtracting. The infinity minus infinity will not occur here. So that is the only problem we have to avoid. Then define and suppose. No, that's okay. We don't have to take it. Then and phi equal to summation lambda I 1 for measurable set. Here is we assume there is a sigma algebra behind. Here is in the sigma algebra, and lambda I are numbers from 0 to infinity. Then define integral over x phi of x du mu x. So let's assume we have a measure space x this this is equal to summation just lambda I. That's all. Okay. If we have a simple function, summation I equal to 1 to n, lambda I 1 ei, then we define its integral to be just I equal to 1 to n, lambda I, the measure of the set. That is, in particular, we are just defining integral of this 1e over x g mu to be just measure of that. Okay? Then we are extending it linearly to simple functions. Okay? Just a linear extension. So one thing we have to verify is any simple function can be written as several possible ways like this. So it does not depend on the partition. I mean, these EIs forms a partition of x. Okay, that is EI. This is disjoint union, which was defined earlier. This is equal to x. So suppose if we have two disjoint union, then the integral is well defined. That's what. So the first verification claim this integral phi d mu over x does not depend on the partition. Okay, that is, suppose phi equal to summation I equal to 1 to lambda I ei is also equal to summation j equal to 1 to mu I f mu j f j. Suppose we can write it like this, the same phi, then we have to get the same integral, same value. That's what it means by well defined. Okay. Then what happens? Then lambda I equal to mu j on ei intersection of j, right? Because it's the same function. Okay. And sorry, this has to be 1. So, is this okay? You got lost or something?
So are we assuming that the partition, so both the partitions are disjoint, right?
What do you mean by both the parts? They are partition.
Like,
what do you mean by they are disjoint?
Okay.
There is nothing disjoint like that. They are just
Yeah.
two different partitions. That's all. I don't know why is it going to the top. I'm not touching anything. There is nothing like disjoint or something. We have two partition, okay, and we are writing the simple function with respect to two partition, which is possible, of course. You can take, you can divide the set into two things and do something. Okay, I mean it's because of the additiveness of the measure, the integral should be same. The integral is also in some sense additive. You can integrate over one set and you can integrate. I mean, we are defining integral over the whole x, but we can define it on a set also, which I will define after this. So when we have two different partition ei and fj, suppose if we can write phi with respect to this partition ei and with respect to fj, then the integral should be same. That's what we want to say. Before that, we notice that lambda a equal to mu j on ei intersection fj. Okay, I mean, suppose x is in, right? Since what is there? Phi of x. I mean, it's just the phi of x. Phi of x should coincide. Okay, the two values of phi of x should coincide. There is no meaning for this.
So you are not assuming that the lambda is a disjoint? I mean distinct?
Case are disjoint.
No, the values lambda is, they need not be disjoint, right?
What do you mean by lambda I values are disjoint? Different, you mean? Lambda
So
is a number.
Yeah, so the you are assuming that lambda is not equal to lambda j for I not equal to.
No, there is no need. We are not assuming.
Okay.
There is no need for that.
Sir, will you please scroll up a bit?
Yeah. This is okay. Now, what do you want to see? You want to see the definition of the integral?
Yes, sir. Like I wanted to see that, but also like how we said the phi is like, so
How
like
the
while like like what is the nature of phi at least, as in like the
phi is a simple function. Okay. So a simple function, we are writing it with respect to some partition, some disjoint sets, EIs. Okay.
okay.
I
I
mean,
wanted
any
to
simple function can be written like this. No? Any simple function can be written like this, wherever I circled. So any simple function can be written like this, right? So using this representation, we are defining the integral like this. I mean, sorry, any simple function can be written like this. I'm sorry. You see.
So in the definition, are you assuming lambda is to be non-zero?
No, no need. Lambda
So,
is can be anything between infinity to 0. It can be 0.
but what if lambda is zero and mu of ei is infinity? Like,
0 times infinity is in 0 for us. Yeah, correct. We have to
okay,
assume 0 times infinity is 0. Mu is infinity, then 0 times infinity is 0. Right. Yeah,
okay,
that is we are assuming. So good point. So 0 cross infinity equal to 0 for us. Okay. So we are assuming that. That's right. Now even lambda can be infinity and the measure can be 0. That's also possible. So then also it is 0. Okay. There may be a set of measure 0 where this phi can take the value infinity. Okay. So that's also possible. Okay. So then we are defining the
Sir, you need to avoid this infinity minus infinity kind of things, right?
yeah, but there is no
Or okay, you are taking all positive things or non-negative things.
exactly. We are taking only positive measure. Lambda i's are between 0 to infinity. There is no problem.
Yeah.
Okay.
Yeah.
So if the only thing we have to avoid is infinity minus infinity. So for that only we will do something. We will define an integrability condition. Okay. Okay. So now this is okay. So this is what we have to verify that the integral is well defined. Suppose if we have two partition EI and FJ and phi can be written as summation lambda I phi, lambda I 1 EI and mu j 1 Fi summation. Then we have to verify that the whatever the integral we have defined, that is same. To verify that, we first notice that lambda I equal to mu j on this. Okay. Then and summation lambda I mu ei equal to you should remember that the EIs are disjoint and FJ is also disjoint, which is equal to summation lambda I. This can be written as summation j equal to 1 to m mu of EI intersection FJ. Right? You can write it like this. Okay, because FJs are disjoint. Okay, so that is equal to this is I equal to 1 to m. Okay, so the whole thing will become summation I equal to 1 to n summation j equal to 1 to n lambda I mu of EI intersection FJ. I mean, if you notice, I have followed one step. I have to write the disjoint union inside here, and then I have to take it out as summation. But I have directly written it like this. Okay, which is okay. Now you can interchange the sum, which is only a finite sum. You can interchange A equal to 1 to n. And you know that on EI intersection Fj, lambda I is same as mu j. Okay. Oh, there is two mu, but remember that mu is measure. This mu j is a number. Okay. I should have used A, B or something, but that's okay. Okay. Now you can take this summation here inside, and you will find that this is same as j equal to 1 to 1 mu j mu of this EI will go. I will go. Yeah, I will go, and you will get only Fj. Okay. So this integral phi d mu is well defined. Does not depend on the partition. Okay, is fine.
Yes, yes, sir.
Okay, the second claim is
Partition
yeah.
need be
Someone
sir,
say it.
sir, okay, nothing, sir.
Okay, nothing. Okay. So then the second remark or whatever, notice, observe or something, maybe proposition. It's a simple function. Okay. Then maybe phi one, phi two, two simple function. Then a integral a phi one. You can just multiply a simple function by a number that is again a simple function by a real number. Okay. And b over x. I'm just saying it's linear. The integral is linear. Integral. This is for all. We take only real numbers. Okay. 0 infinity, so 0 omega, positive real numbers, and phi 1, phi 2 are two simple functions. So this is just very easy. Let phi 1 equal to, maybe I will write it with, I will avoid mu. A, B, C, what's that letter I will use? AI, 1, phi 2 equal to summation j equal to 1 to 1, dj 1 j. Okay. So one thing is just clear. I mean, if clearly, if you have any phi, integral a phi d mu over x equal to a times integral phi d mu. Okay, that is just clear. Because if you multiply by that, each lambda I, whatever that is defined here, that will get multiplied by a, and you can take the a out and you will get that. Okay, so it says again the meeting will end in 10 minutes. We will end the class after that. If it ends, I will just finish this and stop the class. We'll do it next time. It is irritating to do it again. So we only have to verify that integral of phi 1 plus phi 2 is integral phi 1 plus integral phi 2. That's what we have to verify. So I will just quickly verify this. Integral phi 1 plus phi 2 d mu x equal to, you know what the value is. So we can do one thing. Okay, I will go the other way. Integral phi 1 d mu is integral phi 2 d mu over x. That is equal to summation lambda I mu, I used a. Okay. Ai mu of ai summation bj mu fi fj, right? Okay, j equal to 1 to 1. But then you can write this mu ei again, like you can take the integrate, you can take the intersection, or you can actually, I mean, you can, without loss of generality, you can assume that they have the same partition also. You can assume by repeating the AA or repeating the BJ, that also you can assume. Whenever you have two simple function, you can, by taking the intersection, you can take the same partition for both the simple function. But let us just do it here like this. Summation I equal to 1 to n, summation j equal to 1 to m, ai mu of ei intersection of j. Okay, you can write it like this. Similarly, you can write the same thing again there also. Summation bj can write it like this, both of them. So then you will just get ai plus bj. So you will just get summation I equal to 1 to n, summation j equal to 1 to n. You will only get ai plus bj on mu of ei intersection ej. Now that is the partition. This ei intersection fj, that is the partition for phi plus phi1 plus phi2. Okay. So then you will get phi1 plus phi2. I mean, since phi1 plus phi2 equal to ai plus bj 1 ei intersection fj. That's clear. Anyway, convinced.
Yes.
Yeah, this is very easy. So the integral does not depend on when you define it for simple function, it does not depend on the partition. And if you have two, I mean, and the integral is linear. Okay. Now using the approximation, what we have done, I mean, we can approximate any positive measurable function by as a sequence of simple function. So using that, we will define the integral, and we will have to show that it is again well defined, it is again linear, and all those things, and we will study the property. So we will do it in the next class, and because it may end in few minutes, we will meet next Tuesday. Okay. Okay. If you have any doubt, you can ask before the meeting ends. So if no one has any doubt, I will end the meeting. Okay, goodbye.